Right, so hello, hope you had your coffee and are ready for the next section of the talks. I'll start my talk by saying that I absolutely love TypeScript. So it's one of my, if not the favorite language of mine to use and learn about. But I will admit, there are times when it feels like TypeScript's only goal is to delay my release at all costs. And what do I mean by this? I mean that my code is working, there are no real errors in the code, but for some reason, TypeScript complains, so my build fails, my CI fails, and I can't make the release. So what do? Well, I reach for some of these bad boys and just start slapping on any STS ignores, casting stuff all over the place until I make my build pass. And sure enough, they do help me. But I know it's a hack, right? So I promise myself, and I promise the rest of my team, that I will do it right, just as soon as we make this release work. Now, whether this happens or not, that's an entirely different story, but I'm guessing that the story sounds familiar. Has anyone done something similar in the past? So, yes, exactly. There's a lot of hands in the air here, which is because TypeScript, as wonderful as it is, it can be pretty frustrating. But with the right perspective, all these tiny frustrations, they can stop being frustrations and they can become points of appreciation with the right perspective. So let's start with a story about perspective. Imagine that you live in a cave and your neighbor in this cave is a dragon. Now you and this dragon, you two don't always get along. And this is mostly because on some days, the dragon randomly starts spewing fire all around your cave, which naturally makes the cave pretty hot, and it makes you pretty hot. So you dislike the heat, and you start disliking the dragon. But you don't know the full story, because the dragon isn't just spewing fire randomly for nothing. It's actually using its fire to protect you from a dangerous horde of zombies trying to get into your cave and eat you. But you know nothing about this, right? All you feel is the heat and all you see is the fire. Well, in this analogy, you are you, the dragon is the TypeScript compiler, and as for the zombies, they're all the stuff TypeScript thinks about and protects us from, and I'm not just talking about type checking, all the stuff TypeScript protects us from without us even realizing, which is what I will discuss today. The title of the talk is Treat the Compiler with Compassion, and after you hear it, that's exactly what I hope you do. Now, what do I care how you treat the compiler? Well, it turns out that I'm a big compiler fanboy. I got hooked making my own languages in college, and today I work at Wasp, which is a full-stack web framework that also features a compiler of its own. So safe to say, I like this stuff, right? I'm big on programming languages in general, mostly Haskell, which I teach, and TypeScript, which, like I said, I probably use most often. But getting back to our topic, when I'm working with TypeScript, I don't always look like this. Sometimes I look more like this. And this is not a good look for me, right? No one wants to look like this. So I decided to get to the bottom of it and actually figure out what is it with TypeScript that makes me so mad when I work with it. And I want to share some of what I've learned today with you. So what's the first step if we want to avoid looking like this? Well, we have to ask ourselves, why do we get mad in the first place? And the answer to this is simple. We get mad because we don't get what we want. And we want a lot from TypeScript. In fact, we want much more than is probably good for us. And as you can see from the circles here, TypeScript often knows what's good for us better than even we do. But I'm getting ahead of myself. We'll get to that later in the talk. Let's first analyze what exactly we do want from TypeScript, or at least what we think we want. And to do this, we'll look at a simple example. So this here is valid, syntactically completely valid JavaScript code, but it has one tiny error that will crash it in runtime. Raise your hand if you can see the error. Try to spot it, and when you find out, raise your hand. I'll give you a couple of seconds. Right, so a lot of you noticed the error. It's a classic typo. Instead of a month, we asked for a moth. We expect TypeScript to flag this error, like this, and then when we fix the typo, we expect TypeScript to remove the error, like that. There's nothing groundbreaking so far, right? So if there are type errors, TypeScript should report them. and it shouldn't report type errors that don't exist. Sounds pretty basic, but the last one sounds most basic of them all. So we don't want TypeScript to crash or hang. We always want it to give an answer whether a program type checks or not. These three properties are the stuff we want. So again, either tell me there are errors that exist, don't invent errors that don't exist, and always give me a verdict. So it's safe to say we want them consistently, which just means that TypeScript should always report all type errors. It should never invent type errors, never give out false positives, and it should always give a verdict and never crash or hang. Now take a moment to look at these three properties and think whether they make sense. And you might think to yourself, well, this doesn't really sound like much. In fact, it sounds like the bare minimum you'd expect from any piece of software, especially something that calls itself a compiler. But as it turns out, these properties are much less common in compilers than you may think. And we even have a fancy mathematical term to describe each one of them. So for example, if a compiler always finds all type errors, we say the compiler is sound. If it never invents type errors, and never gives out false positives, we say that the compiler is complete. And if it always gives a verdict for our code, whether it type checks or not, and never crashes, we say it is decidable. So these three things, it's useful to plot them with a Venn diagram because it helps us categorize different programming languages into different groups. So once again, sound compilers always report all type errors, complete compilers never report false positives, and decidable compilers always give a verdict and they never crash. I'll give you a couple of examples where some languages fit on this graph. So for example, Go fits right here. Go's compiler is sound and decidable, but is not complete, which means that Go always finds all type errors in compile time. It always gives a verdict. It never fails to give a verdict for your code, but it sometimes reports false positives. A newish language, very cool for systems programming, Zig, is sound, but isn't decidable or complete, which means that it always reports all type errors if it gives a verdict, but it doesn't guarantee a verdict, and it occasionally reports false positives. And now it's your turn. I want you to think for a few seconds and imagine where on this graph here you expect to find TypeScript. So think about your day-to-day work and how TypeScript behaves and decide where exactly you think it fits. Raise your hand if you think you know the answer or when you think you'll find out the answer. Okay, I don't see a lot of hands, but I've been going on and on about how great TypeScript is, so it only makes sense that TypeScript actually fits right here. So completely outside of everything we've discussed as desired properties of the compiler so far. It sounds ridiculous, but when you think about our definitions, what does it really mean? Well, it means that TypeScript often reports type errors, but might miss one here and there. It means that it occasionally invents type errors that don't exist, and it means that it sometimes even fails to give a verdict and spins infinitely when you ask it to type check a program. It sounds crazy, but when you think about it again, it kind of aligns with our frustrations with the language. Because we get mad either because we get an error in runtime TypeScript was supposed to catch, which happens because TypeScript is not sound, or we get mad because we have to convince TypeScript that working code is in fact working code, which happens because TypeScript is not complete. Or they happen because we straight up don't get a verdict from the compiler. So it fails to tell us whether our code type checks, which happens because TypeScript is not decidable. Now, something to clear up about decidability. I don't mean that the compiler has a bug and it fails because of a bug. I mean that TypeScript's type system is so powerful that it's mathematically impossible to make a compiler that actually always guarantees a verdict on whether the program is correct or not. The technical term for this is that TypeScript system is Turing complete. But this is a whole talk in itself that I might give out someday, and since decidability is really an edge case and you really have to go looking for it to find a case where the compiler fails to give a verdict, we won't be discussing it today. I am happy to discuss it after the talk, so please come and talk to me. The first two though, soundness and completeness, they are pretty common. And at the beginning of the talk, I promised you that I was gonna convince you that these two are not flaws, but that we are actually happy to have them. I still stand by this. So let's start with the more outrageous one and explain why TypeScript is not sound. In other words, why doesn't TypeScript catch all type errors in compile time? Now, when I first heard that this was the case, I was sure it was an accident, right? So the team was working on TypeScript. Someone accidentally pushed a change that broke the compiler and denied its soundness. And by the time they noticed, the change was already out, it was too late, and now we're stuck with a compiler that is not sound. But actually, no. The story is much more interesting than this, because TypeScript is not sound on purpose. And this is not an afterthought or an excuse they came up with. It was actually the plan from the beginning, which I can prove. I don't know if you know this, but TypeScript actually has a list of known goals on their GitHub. So this is just a bunch of stuff that the developers of TypeScript set out not to do from day one. There's a bunch of stuff here, but I want to draw your attention to the third point, which clearly states that they didn't want to develop a sound and provably correct type system. So it truly was the plan from the beginning. But I mean, we have to ask ourselves why. They're creating a language with the sole purpose of catching errors in JavaScript, but right from the get-go, you decide that you don't want to catch all of them. Why would you do something like this? It seems ridiculous. Well, I mean, you can probably guess the answer, because usually in technology we have the same answer, and the answer is that it's a trade-off. And to explain what exactly we're trading off, I'll show you an example. So imagine that you're modeling countries, and each country has a name and a capital. Except our model is wrong already, because some countries, in fact, do not have capitals. So we have to make the capital nullable. Now, I know you're all wondering which country doesn't have a capital, so if someone knows this, they can raise their hand and yell it out. It's only, who said it? Raise your hand. What did you say? Malta. No, actually, Valletta is the capital of Malta. Any other takers? No, Vatican is also Vatican. No, they have 3 of them, actually. But you're kind of exhausting my knowledge. I don't know so many capitals. No, Liechtenstein, it's Vaduz, I think. Let me motivate you. So if you get it right, I'll give you a B. No, Andorra is Andorra la Vella. Monaco is Monaco. Or Monte Carlo, I'm not sure. No, somebody already said Vatican. How did no one Google it so far? I'm disappointed. I expected you to cheat. Yes. Sorry, that's exactly right. So it's a small island nation in the Pacific. They're the 3rd smallest country. They don't have a capital. Congratulations. He doesn't want to be. So I'll just throw it in the audience, and whoever catches it gets it. That was very gentleman of you to block me in front of the lady. Right, so getting back to TypeScript, actually. This is our model of a country, and now let's create a function for making some travel plans. So let's call it try to going to capital off. The function takes a country. Does this have a pointer, perhaps? I don't think so. Okay, never mind. It takes a country and checks whether the country has a capital. If so, it applies for a visa and tells us where we're going. If not, it doesn't do anything. We can call this function. Oh, by the way, the apply for visa function just does some serious visa stuff, whatever that means. So we can call this function either with countries that have capitals, like Macedonia, or countries that don't have capitals, like Nauru. Let's see if our example works so far, and then we'll try to break it. Right, so this is the same code we had on the slides. And let's talk about what we expect to see. For Macedonia, we expect to see going to Skopje, exclamation point. And for Nauru, we expect to see nothing. There was kind of a spoiler in the console from before. So I run the code, and I see going to Skopje. So exactly what I expect. Why does this work? Well, it works because even though capital can be either a string or null, at this point in the code, move yourself. At this point in the code, we check for the null option and eliminate it. So throughout this entire block, TypeScript actually knows that capital can only be a string. This here is called a type refinement, and the entire process of the compiler doing this is called type narrowing. And you're probably familiar with the system if you use TypeScript. It's very useful, saves us a lot of boilerplate without us having to even do anything. And of course, if I do something like this, TypeScript recognizes the error because it can no longer be sure that the capital is a string. In fact, it can be sure of the exact opposite. The technical speak for this is that this assignment invalidates this refinement. So far so good, right? TypeScript is still sound. It successfully caught all type errors it could have caught. But watch what happens if I move this line into this function right here. There are no complaints from TypeScript. And sure enough, if I run the code, I get a type error in runtime. So this capital is null, but TypeScript still thinks it's a string. And this is a textbook case of the language not being sound. So if you remember the definition, we have a type error, but the language fails to catch it in compile time. Now, I told you this was done on purpose, so the first question we should ask ourselves is whether TypeScript could have protected us against this type error. And the answer is absolutely. So what could have TypeScript done? It could just say that as soon as you call a function with a mutable object, all type refinements made for that object are invalid. So function calls could just invalidate all type refinements we've made and reset the object to default settings. But they decided not to do this. And they decided not to do this because this pattern, where you check for something and then call a bunch of stuff to process it, is so common in JavaScript, while this thing here, where you actually change the field of an argument, is so rare, or at least you want it to be rare, that the team decided they didn't want to make 99% of the code more verbose, just to save you from this one specific edge case that you shouldn't be even doing in the first place. And to drive this point home, let's go back to our slides and think about how this function would look like if function calls like this one actually did invalidate refinements. So you would have to check whether the capital is null again after each function call. And it's not so bad when there's only a single function involved, but when you have multiple functions like this, and again, this is very, very common, it can get pretty ugly. So the trade-off was made. The team decided to risk some correctness for a lot of practicality, and TypeScript ended up not being sound. But this is far from the only example of it. So TypeScript is full of these kinds of practical trade-offs that sacrifice correctness, and I could go in for hours talking about all the bugs I thought I found in TypeScript, only to figure out that it was actually a very deliberate decision that actually serves me. I'm far from the only one, though. So this is so common that the TypeScript team actually has an FAQ page where they list all the common bugs that aren't bugs, because they keep getting reports from people that mistake these trade-offs as shortcomings of the compiler. And before filing an issue with TypeScript, they make you read this page to ever so slightly reduce the number of reports they're getting. Each item on this page comes down to the same thing. So finding a balance between soundness and practicality. And it's very useful to think of this as a dial. So when you're using JavaScript, there's no soundness to speak of because you don't have a compiler and you don't have a type system. So the dial is all the way down to the left. As soon as you activate TypeScript, the dial jumps to the right. You get a lot of checks. But with the default compiler settings, TypeScript still tolerates a lot of stuff too. Of course, the team knew this, so they included some knobs and some switches that help you control the dial according to your preferences. So for example, you know these switches as strict mode options. Activating all strict mode options moves the dial even further to the right. And if that's still not enough for you, if you want to risk even more practicality to get even more correctness, you can use some of the options outside of strict, like unchecked index access, to move the dial even further. And this is strict options and some other options that aren't included in it. That's the best you can do with TypeScript. But what else? Another thing you can do is bring in some extra help, like TypeScript ESLint. And TypeScript ESLint has a family of options called no unsafe. When you activate these things, TypeScript ESLint actually checks for more stuff, and the dial even moves even further to the right. If that's still not enough for you, you can use something like tsreset, which overrides some of TypeScript's core type signatures and makes the language even safer to use. But even with all of this machinery in place, so TypeScript ESLint and TSReset, this example would still fail to warn you about the error. Hopefully, though, after we've seen the example earlier, I've convinced you that you probably wouldn't even want this to warn you. If you're still on the edge, just remember this monstrosity and imagine it living in your code base. Perfect. So hopefully now we understand soundness trade-offs. We know that the authors risk correctness to give us practicality. But what about the other way around? Why do we sometimes have to convince TypeScript that working code in fact works? Why does TypeScript throw false positives? I won't tease the answer this time. I know you already know it's a trade-off. So let's explain what we're trading off through an example again. Say you have two functions, again, according to our country theme. One for setting the population and another one for setting the language. You might do something like this if you come from JavaScript. So set the population to data, call the function, set the language to data, call the function. The code is 100% correct, but as soon as you activate TypeScript, you get not one, but two type errors. Why? Well, because TypeScript considers data to be a number. So later when you try to assign string to data, TypeScript, of course, complains. But, I mean, the code works. So why can't TypeScript see it? Well, you can make TypeScript see it, but it's going to require a little bit of compiler wrestling. In this case, it's not too much. It's enough to tell TypeScript, hey, I want this here to be either a string or a number. And you do that with a type declaration, such as this one. When you do this, TypeScript knows all it needs to know, and the errors just go away. So the obvious question is, why did I have to do this? Why couldn't TypeScript have figured this out by itself? I mean, could it figure it out by itself? And the answer is, yes. Again, it absolutely could, but it was decided it shouldn't. So what could have TypeScript done? It could have done the same thing we did. So it could have looked at all the ways we use the variable and say, hey, this guy is first assigning numbers to data, he's then assigning strings to data. Obviously, he wants data to be strings or numbers. So why didn't it do it? Like we said, it's a trade-off, and this time, it's a slightly different trade-off. So there are two reasons for this. The first reason is that code that uses complex type inference and looks at all the ways a programmer uses a variable is actually more difficult to reason about and more difficult to compile. So they sacrificed power to make the compiler simpler and to make reasoning easier. But the second reason is actually much more interesting. So the authors of TypeScript decided that they can use the TypeScript compiler to teach people how to be better at coding. This pattern, while very common in JavaScript, is also a very common foot gun. So you don't really want people to be using a mutable value that's imprecisely named for all kinds of different things. So the team decided, let's use the compiler to actually nudge people into the right direction of coding. And this is amazing to me, because the compiler doesn't necessarily do only type checks. It only gives you opinions on how you should be writing your programs. So it doesn't really want you to do this, because this is ugly. What it really wants you to do is this. So it wants you to use proper names and proper variables for different things. Not this, this. And of course, in the real world, you wouldn't have hard-coded values. You'd have an API call or something that returns the actual value that you're using. But hopefully you get the point. The point being that TypeScript isn't really bullying you for no reason. It's actually giving you some tough love and teaching you how to become better at what you do. Like I said, it's all a matter of perspective. Hopefully now we understand both of these, and we've seen two trade-offs. So one sacrifices correctness for practicality, the other one sacrifices power for quality and simplicity and learning. But there's one very important thing I need to emphasize, and that's that knowing about this kind of stuff does not give us a TypeScript is stupid pass. So we shouldn't just go around casting stuff left and right and thinking, oh, TypeScript is being unsound again, TypeScript is being incomplete again, it knows nothing, I know better than TypeScript knows. Because at the end of the day, most of our frustrations with the language actually come from the fact that we're misunderstanding it. And I'll give one final example for this as well. It has something to do with the object.keys function. Who can guess what I'm going to mention? It's a very famous example. Okay, a couple of hands. Okay, it's actually good, because if you don't know it, you're going to learn something new. back to our country theme. We have our countries. This time we want to log them. So we want to implement this log country function. The function takes a country. It iterates over all keys of the country object, which means a name and a capital. And then it console logs each one, right? Sounds good? Doesn't work. Immediately when you write this, TypeScript says you have an error. Why? Well, because TypeScript decides that country keys here is actually a string array. And you can't use a generic string array to index an object with known keys. But why doesn't TypeScript do something like this? Why doesn't it conclude that since you're indexing a country, this array can only include the keys of a country object? Is this another case of TypeScript throwing out a false positive, or is something else going on? Well, as it turns out, in this case, TypeScript is 100% correct to complain. Because this type signature here, it can't really enforce what this object doesn't have. It can only enforce what the object does have. So it needs to have a name and a capital, but it can also have anything else. For example, the population of the country. And this is thanks to something called a structural type system that the TypeScript uses. So the caller of the code can call the code with a richer object than the one specified in its type signature, as long as it doesn't break this contract. So in reality, when this line is being executed, TypeScript has no idea what else besides a name in the capital is inside the country object, and this would be the wrong thing to conclude about the type. You have to infer that this variable here includes a string array. There's a bunch of this stuff. So this isn't the only example of such surprising behaviors, and I can't cover all of it in a single talk. By this stuff, I mean behaviors that make perfect sense, but only once you actually take your time to understand them, right? So this was kind of a teaser to show you what's out there, and maybe if you're interested, you should explore it for yourself. What I can do is recommend you a book. It's called Effective TypeScript, and it's written by Dan van der Kam. So it's an amazing book. I've read it 2 times, and a couple of chapters I read all the time. And whoever is working with TypeScript, I think, should read this book. Very practical, full of examples, and just enough theory to really make you understand the examples it gives out. Until you do read the book, just remember this. Yes, TypeScript is not sound, which means that sometimes it will fail to catch a type error in compile time. It's not complete, which means that sometimes you will have to convince it that working code is in fact working. But most of the time, TypeScript still has our backs. It's protecting us from stuff we might not even realize, and we are the ones who are not seeing the bigger picture, while the compiler is our friend. Thank you.